Welcome all. So in continuation to our numericals on steam turbines, let me take up some more questions, and this topic is very important both from GATE and engineering services point of view. So in the first set I solved around 16 questions, and let me complete remaining questions. Okay, now throttle governing in steam turbines. You know that irrespective of the load, we control the speed in governing. So actually there are different types of governings. In throttle governing, actually what we do is the steam is throttled. For example, let me take enthalpy here and entropy. These are, let us say, constant pressure lines. The steam is throttled. For example, let us say this is the expansion 1 to 2s, but the actual expansion is irreversible, so let this be 0.2. In throttle governing, what we do is we throttle. For example, now I want to reduce the power developed. So you know the power is given by m dot into delta H. Either you regulate delta H or you regulate m dot. Now see, in throttle governing, what we do is we throttle the steam from high pressure to low pressure. Therefore, let this be 3. Now from here it expands. Let this be 4s. Let this be 4. Look at, my dear students. In this case, you are getting more power, but if it is throttled, so due to reduction in enthalpy drop, so the power developed is less. So therefore, there is a pressure loss. The throttle governing leads to significant pressure loss. We are throttling from P1 to P2. Therefore, the value of P1 is more, P2 is less. So therefore, there is a significant reduction in pressure loss. So throttle governing leads to, in fact, actually, it is resulting in reduction in what the available energy. But anyway, we have to govern. So therefore, this is one of the techniques. So therefore, there is a significant reduction in pressure in throttle governing. Chalo, we'll move to the next question. Blade erosion in steam turbines takes place. Look at, my dear students. We know, let us say the steam is expanding, say from 1 to 2. If the drainage fraction is less, you know the liquid content will be more. And the velocities are very high in turbine. The liquid, due to high density, and thereby it impinges, it erodes blades. So therefore, due to the droplets in steam, water droplets in steam, it is leading to significant reduction or erosion of blades. So therefore, due to droplets in steam, there is a erosion of turbine blades which is taking place. That's why we keep the drainage fraction very high, which can be done by using reheating. Okay, chalo. Next. Now, which of the following are correct with respect to impulse turbines? With respect to impulse turbines, blade passages are of constant cross section. In impulse turbines, it is something like this. The passage is constant, but whereas in reaction turbines, they are aerofoil types, and the flow is the passage area, they are of nozzle type, and this is decreasing. So he's asking about impulse turbines, therefore the flow area is constant. Yes, the first one is correct. The flow area is constant, so therefore one is correct. Now, the partial admission of steam is permissible because, you know, my dear students, in case of impulse turbines, the pressure remains constant, but whereas in reaction turbines, the fluid enters at high pressure, therefore it should run in full. So in impulse turbines, as the pressure is remaining constant, so the partial admission, even we have seen in Pelton wheel. In Pelton wheel, if you see, it enters at atmospheric pressure, therefore this casing has no hydraulic function to perform. So therefore, as the pressure is remaining remain constant, the partial admission is permissible. Now next, you know, my dear students, axial thrust is due to change of velocity, flow velocity. So you know the axial thrust is given by m dot into vf1 minus vf2. This is, it is due to change of flow velocity, therefore 3 is also correct. So therefore 1, 2, 3 are correct. So the axial thrust is due to the difference in flow or axial velocity. That's why generally to nullify the axial thrust or to keep the axial thrust to minimum or to keep it to 0, generally the flow component is kept same. So when vf1 and vf2 are same, therefore you get the axial thrust 0. Okay. Now in reaction turbines, the enthalpy drop in a stage is 60 and the enthalpy drop in moving blades is 32, and he is asking degree of reaction. Okay. The degree of reaction is actually, it shows how much enthalpy change is taking place in a rotor or moving blades with respect to the total enthalpy change in a stage. Stage comprises of moving as well as fixed blades. So therefore, so the enthalpy drop in moving blades to the enthalpy drop in a stage. S stands for stage, M stands for moving blades or rotor. And but we know that the stage is given by, the stage is nothing but moving plus fixed. The stage is nothing but moving plus fixed. So therefore now the total stage is given as 60. Therefore the enthalpy drop in a stage is given by enthalpy drop in moving plus enthalpy drop in fixed. Okay, so now observe here, the enthalpy in a stage is 60 and moving is given as 32 and fixed we don't know. Let us calculate the enthalpy drop in fixed. It is 60 minus 32, I think it is 28, correct na? 28. So therefore the degree of reaction is given by, there is no need to calculate, so directly it is given, just I have shown in the moving blades, directly it is given as 32. There is no need to calculate this, but anyway I have shown you, this is the extra part which is not at all necessary in this problem. Enthalpy drop in a moving blades is already 32 and stage is given as 60. So therefore let me calculate 32 by 60. It is 0.533. Where is that? Yeah. So and if he asks you what is the enthalpy drop in a fixed blades, it is 28. It is 28, which is not necessary in this problem. Okay, right. Now we'll move to the next. Similar question. The enthalpy drop in a moving blade is 10. And the enthalpy drop in a fixed blade is 15. What is the degree of reaction? So you know it is nothing but enthalpy drop in moving to the enthalpy drop in a stage, but stage is nothing but moving plus fixed. So therefore moving is 10 and this is moving is 10 and fixed is 15. So therefore 10 by 25. Okay na? So into 40 I think, 40%. 10 by 25, it is 10 by 25, 40. So therefore it is 0.4 or 40%. Where is that? Yes, this is 40%. Okay, next. Now, consider the following statements with respect to steam turbines. Dekho. A single stage impulse turbine has the nozzle angle alpha. The maximum blade efficiency will be cos square alpha. Yes, actually he should have used the word ideal impulse turbine, so it is cos square alpha, correct, but it is ideal, so no problem, it is taken, so it is cos square alpha. If it is not ideal, it will be 1 plus k cos square alpha by 2. So first statement is correct, so therefore the maximum impulse turbine efficiency is cos square alpha. For a reaction steam turbine with identical stator rotor blades, the maximum efficiency is equal to inlet steam velocity. The blade velocity is equal to, let us see the second statement. for a reaction steam turbine with identical stator and rotor blades, the blade velocity, let us say U, is equal to steam velocity, inlet steam velocity means V1. He gives, let us check the validity of this statement. You know, I have derived an equation for the maximum efficiency for reaction turbine, 50% reaction turbine. So the condition for the maximum efficiency is the blade speed ratio rho, which is U by V1, is equal to cos alpha 1. So therefore U is equal to V1 cos alpha 1. But yahan pe he gives it as U is equal to V1. But actually, in fact, the blade speed is V1 times cos alpha. So but he says U is equal to V. So this statement is wrong. Second is wrong. Where is that? Ye gaya, ye gaya, ye gaya. Khatam hai. That's it. Velocity compounded impulse turbine gives less efficiency. Actually, compared to, it is actually compared to pressure compounded. So yes, it is correct. So therefore 1 and 3 are correct. So yes, velocity compounded will give me less efficiency. I explained why all those in my regular class. So let's move to the next one. The optimum ratio of blade speed. So rho is equal to U by V1. The tangential component of jet speed, that is blade speed, for the D level, you know, D level is a simple impulse turbine. So rho is equal to cos alpha 1 by 2, and therefore U by V1 is equal to, where is that? Optimum blade speed ratio is, okay. It is U by V1 is 1 by 2 cos alpha 1. This is for what? Impulse D level likhenge. D level. I'll write DL as D level. Okay. Now for rho is equal to cos alpha. This is for Parsons reaction turbine. So I write U by V1. This is Parsons. P stands for Parson, is equal to cos alpha 1. Wonderful. So now I write U by V1 for D level is half of cos alpha 1. What is cos alpha 1? U by V of Parsons. Okay, Parsons. So can I say that the blade speed ratio of D level is half times the blade speed ratio of Parsons? Let us check. One for both, galat. Half for D level and one for, okay, half for D level. Okay. Actually, he has missed the angle. No problem. Half for D level and one for Parsons. One for D level. Ye galat hai. So D level is half of the Parson. Okay. So therefore, half for D level and one for Parson. Okay. This is the right suitable answer. It is half for both. Galat. So for D level, it is half of the Parson. Okay. Fine. Now let us move to the next one. What is he saying? In half degree reaction, means the degree of reaction is given as 50. देखो एक बार, the degree of reaction is equal to enthalpy drop in moving to the enthalpy drop in a stage. Stage is nothing but moving plus fixed. How much is the degree of reaction given? Half. What does it mean? So half, the degree of reaction is half, is equal to enthalpy drop in moving to the enthalpy drop in moving plus enthalpy drop in fixed. So therefore, enthalpy drop in moving plus enthalpy drop in fixed is equal to 2 times enthalpy drop in moving. So therefore, enthalpy drop in fixed is equal to, let us take this to this side. So 2 delta Hm minus delta Hm. So you are getting this as delta HF is equal to delta HM. So for 50% reaction, obviously we know that the velocity triangles are mirror images, symmetric, and the enthalpy drop in moving and fixed blades is exactly same. It is exactly same. So therefore, the answer is, where is that? 1 second, please. Excellent. Yes. Right. So enthalpy drop in one stage occurs. So half in fixed, half in moving. So it is correct. So entirely in the fixed blades is wrong. Entirely in moving is wrong. None of the above. So half in fixed, half in moving blades. So C is the right answer. Next. The total power developed by a 3-stage velocity compounded impulse turbine, the total power is 900 kilowatt. But clearly he said it is a 3-stage velocity compounded turbine. For a 3-stage velocity compounded turbine, so mark this question as very important. For a 3-stage velocity compounded turbine, the work is split like this, 5:3:1. If it is a 4th-stage, the work will split like 7:5:3:1. So it is a 3-stage now. So the observation is in a Curtis turbine, that is velocity compounded turbine, in velocity compounded turbine, as number of stages are increasing, let us say first stage, second stage, third stage, as number of stages are increasing, the last stage work is decreasing. Let us say if the first stage is developing 500, second is developing 300, third is developing 100. So you know the stages are increasing. So if you are going for one more stage, additional stage, let us say, so 7:5:3:1. What does it mean? You have gone for one additional stage, but the subsequent last stage is giving me less work. That's why we don't go for many stages in velocity compounded impulse turbine. The reason is additional cost is increasing with the addition of stage, but I'm not getting the work in the last stage. The work is getting reduced. So therefore, you should be very careful. Second, please. Now let me remove this. Okay, so fine. Let me erase. Chalo. Let us find out what is the total. 5 plus 3 is 8 plus 1 is 9. So first stage work is 5/9 into 900. Ye add karna. This is the ratio. 5 plus 3 is 8 plus 1 is 9. So first stage work is 5/9 and the second stage work is, what is the ratio? 3/9 into 300, and the third stage work is 1/9 into 900, because sorry, this is 900, I'm sorry, this is 900. The total work is 900. So now this will give me kitna aa raha hai? I think this is 500. I think this is 300 and this is your 100. So what is the asking? The power developed in the first and second stage. For the first stage it is 500, for the second stage it is 300. So therefore it is 500 and 300. A is the right answer. Wonderful. Next. Consider the following stages. Yes, the blades are of aerofoil shape and the manufacturing is difficult. So one is correct. Now, it is suitable for small power. You know, actually reaction turbines, the power developed is, it has higher efficiency. You can use for bigger also. It is used for suitable for small plants. No. And leakage losses are less compared to friction losses. Look at, my dear students. In reaction turbines, the fluid enters at very high pressure and leaves at low pressure. So if you see the time spent by the fluid in the turbine, it is definitely high pressure. So when the pressure is high, the leakage chances are more. Whereas in impulse turbines, the pressure is constant, though leakage losses are less. In reaction turbines, as the pressure is high, it enters at high pressure, so leakage losses are more. But what is it saying? Leakage losses are less, so it is wrong. So therefore, only one is correct. Now, let's move to the next one. A steam turbine is supplied with steam at a pressure of 20 bar. Okay, gauge, be careful, at 20 bar gauge. After expansion in turbine, the steam passes to the condenser and the vacuum in the condenser, understand carefully, and the vacuum is 250 mm. And what is he asking? The inlet and exhaust steam pressures are. Okay, so we generally deal with absolute scales. Okay, now you know, let us take the atmospheric pressure as 100 kilopascal. or 101, चलो क्योंकि मुझे 1 दिख रहा है यहाँ पे, so I am suspecting something, so therefore कहाँ गया वो, yeah, right, let us take this 101 kilopascal ले लेंगे. Okay, this is atmospheric. And what is the steam pressure turbine is supplied with? Oh, 20 bar gauge. Can I write 1 bar is 100 kilopascal, 1 bar is 100 kilopascal. Okay, fine. Now this is 20 bar, 20 bar, so multiply with 20, तो कितना आएगा? 2000. So it is 2000. But why are you showing from this line? Because it is given as gauge. Whenever I say gauge, it is always relative to atmospheric. Relative to atmospheric, it is gauge. So this is 2000 kilopascal. But now I want absolute. Absolute is from this line. So what is the inlet pressure? It is 2000 kilopascal gauge, or if you want absolute, you add atmospheric. So this is 101. So therefore it is 2000 plus 101, so it is 2101. Oh my god, so these two options can be eliminated. 2101. Okay, now let's go for the exit pressure. Let's go for exit pressure. Now let me erase this. Okay, let's go for exit pressure now. Okay, it is 250 mm of mercury, but clearly he said vacuum. What does vacuum mean? Vacuum ka matlab, it is with this line, and this is given as 250 mm of mercury. Let me convert this in, but I want from this line. So let me find out this, and you know this is absolutely, it is 101 kilopascal. So isko hum Newton per meter square mein let's convert this. Why are you taking from this line? Because it is given as vacuum. So it is this. So P is equal to rho GH. This is given in terms of mercury. So therefore density is 13,600. G is 9.81 and H is 250 mm can be written as 0.25 meter. 250 mm can be written as 0.25 meter, and this will give me in Pascal, that is Newton per meter square. So I am dividing with 1000, so you will get it in kilopascal. You will get this in kilopascal. Let me try. 13,600 into 9.81 into 0.25 divided by, let me divide with 1000. So I'm getting this as 33. So this is nothing but 33.54 kilopascal. 33. So but I want from this line, agar ye 33 hai vacuum, so I want absolute. I want this. So what will be this? So it will be 101 minus 33. So are a vacuum, I got it as 33.534 kilopascal. I want this. So I'll subtract 101. So I'll get this as 67.8. This is 67.8 kilopascal. So it is roughly 68. So therefore it is 2101 and 68 kilopascal. It's a simple basic question. Okay. Next.